So sticky, so slimy.
Hi, my name's Dr. Smith, and I am a chemistry professor here at Brigham Young University. I'm here with you today to celebrate National Chemistry Week, which is the 1 week a year we get to celebrate just how awesome chemistry is. And this year, we get to focus on sticky things. Ooh, so sticky, so sticky. Oh, what a sticky mess. I'm gonna rinse this off so we can do some more chemistry. Get some water, rinse it out nice and well. Oh, look, here's some soap. Here's some soap. Wait a second. This doesn't look like normal soap. Chemistry is magic. So that was a pretty good flame, but here at Y, I think we can do a little bit better.
Because it's National Chemistry Week, and we're talking about sticky chemistry, let's think of some sticky things. What sticky things can you think of? Probably the slime I was just holding, but what else? Maybe white glue, like we use in school. Or Scotch tape. Maybe duct tape, or Post-it notes. Masking tape, glue sticks, or super glue. Whatever sticky thing you have in mind, have you ever wondered why it's so sticky? Let's talk about the chemistry behind sticky things. Stickiness is really just attraction. Molecules can attract, a lot like magnets. Magnets have a north and a south pole, and opposite poles attract. Now, molecules aren't magnets, but they do have positive and negative regions, and as with magnets, opposites attract. We call this electrostatic attraction, the attraction of positive and negative regions of molecules. If we look at real molecules here, the red regions represent negative areas of the molecule. The green regions represent positive. And as you can see, green is attracted to red. Opposites attract. Some attractions are stronger than others. In the example we've seen so far, these two molecules are attracted and staying close, but they're still able to move somewhat freely past one another. This reminds me of two hands being pressed up against each other. They're attracted, staying close, but still able to slip and slide past each other, and even perhaps be separated. This is how a lot of tapes work. For example, masking tape on a painted wall. The sticky part of the tape is attracted to the wall enough that it stays put, but not so much so that you can't separate them. There are other attractions, however, that are so strong, they're more like connections. We call these bonds. All a bond is a really strong electrostatic attraction. We usually draw a stick between the atoms involved to denote just how hard it is to get them apart. If you've ever put super glue on your finger, you've experienced a chemical bond. The attraction between the glue and your skin is so strong that it's almost impossible to break without rubbing your skin off. Just as there are different strengths of attractions, there are different types of attractions. The molecules that we've seen so far all have permanent positive and negative regions. We call these molecules polar. But there are other molecules that don't have permanent positive and negative regions. We call these molecules nonpolar. Nonpolar molecules can still interact and attract one another. They just do it in a different way. They attract through small distortions of their electron clouds that produce temporary positive and negative regions, which are constantly changing. That's kind of hard to imagine, so let's illustrate with a little bit of slime.
This slime, I can distort it any way I want to. That's like a nonpolar molecule. Its electron cloud can be constantly distorted, creating localized positive and negative regions that can attract to nearby molecules. But polar molecules have a permanent positive and negative region. And when polar molecules come close to nonpolar molecules, they don't like it. The nonpolar molecules don't like the polar molecules trying to impose a permanent positive or negative region in them. So they repel. That's actually how your nonstick pans work. The pan is coated with something that's nonpolar. And when you put something that is polar, like water on it, it doesn't stick because they don't play nicely. Another thing that's nonpolar is crayon. If you've ever tried to wash off crayon from, say, a wall, you know it doesn't really work if you use water. You have to find something that's non-polar to really get it to rinse off. Now this is going to take a while, but what I have in this beaker is hexane, and it's a non-polar substance. So after a while, the crayon will start to dissolve because the molecules of the crayon are sticking to the molecules of the hexane. They're both non-polar molecules and they're attracted to each other. And that's why things stick together. Molecules attracting.
As we saw with our crayon and our nonstick pan, nonpolar molecules and polar molecules don't stick together very well. Their methods of attraction are just too different. If you want to try this at home, you can try mixing oil with water. Vegetable oil is nonpolar, while water is polar. You'll see how well they stick together. Now these are great examples of very polar and very nonpolar molecules, but there's actually a whole range of polarity, and most molecules are somewhere in between. So sometimes you can get a nonpolar molecule to stick a little bit to polar molecules. Here's a good example.
So, like we've talked about, nonpolar molecules and polar molecules don't like to stick together. But there's a whole range of stickiness, and sometimes you can get nonpolar molecules to stick a little bit to polar molecules. Here I have some water with an indicator in it, and the air above the water has oxygen in it. Oxygen is nonpolar, so it normally doesn't like to stick to polar things. But if I shake it up and mix in some of the air with the water, I can get some of the oxygen to dissolve for a little while and to stick to the water molecules for just a little while. And once they stick to the water molecules, there's a change that happens that makes the indicator change colors.
This is why we have so many different types of tape and glue. The different types of attractions and different strengths of attractions make it so different materials stick or don't stick to certain tapes and glues. You have to choose the right adhesive for the job, and that all depends on what type of attractions are involved and how strongly you want things to stick together. For example, if you want to stick two pieces of wood together forever, you would use wood glue. It forms a bond. But if you only want to attach something temporarily to the wood, you might consider using masking tape. It'll come off. Now that we know that stickiness is really just molecules attracting, let's talk about glue. How does it work? Well, I'm starting to get hungry and I found something in my lunchbox that can help us. Let's take a look.
I bet you've never thought about it, but a peanut butter and jelly sandwich is a perfect example of glue. You have two pieces of bread, two things that you want to stick together, and you have peanut butter and jelly in the middle acting like a glue. Watch. If I pick up the top surface, it's totally glued together. Now, glue works because of cohesion, the glue molecules sticking to each other, and adhesion, the glue molecules sticking to the two surfaces. So, what makes a good glue is when those forces are relatively equal. Is peanut butter and jelly a good glue? Let's find out. Not that great. What went wrong? Well, it looks like there's jelly on both pieces of bread. I only put it on one piece of bread, so it looks like the adhesive forces are stronger than the cohesive forces. The jelly sticks better to the bread than it does to itself. So it's an okay glue for a sandwich, probably not one that you would want to use for anything else.
As we saw with my peanut butter and jelly sandwich, glue works because of cohesion, or the glue molecules being attracted to each other, and adhesion, the glue molecules being attracted to the two surfaces. So we've talked about how glue works, but what is it? Just what kinds of molecules are capable of this adhesion and cohesion? The answer is polymers, or long chain-like molecules. Let me show you what I mean.
All right, now that we know how glue works, let's talk about what it is. Glues are mostly made up of things called polymers. Polymers are just really long molecules. I like to think of them as kind of a monkey chain, where there's lots of individual pieces that are all the same. We call those monomers, and then they all link up into this really big chain, kind of like when you pull monkeys out of a barrel and lots of them come. Polymer is just a big chain-like molecule. kind of like a monkey chain. Let's make one. Nylon is a polymer, and here I have a solution that we've colored blue, and when I pour this top solution over it, there's going to be a chemical reaction at the barrier between those two solutions. And if I pull on it, the molecules start sticking together and linking up into that big, long polymer chain. And I can wind it around this and just keep pulling. Let's see how far we can pull it. Oh, it's still going. All those little molecules are like monkeys linking arms, making a big, long polymer chain. Let's see if we can make it even taller. Let's see. Whoa, we might lose it. And it just keeps going. What a polymer. And it just keeps going.
Nylon is a great example of a polymer, but it's not a glue, because the monkeys in that chain keep their hands to themselves. In glue polymers, those monomers don't keep their hands, or their feet, to themselves. An example is white glue, which is made of PVA, or polyvinyl acetate. These molecules look something like this. Glue stick molecules are PVP, or polyvinyl pyrrolidone, that looks a bit like this. Superglues are any one of a number of cyanoacrylates, and they look like this. All of these polymers have side chains that are capable of being attracted quite strongly both to other glue molecules and to the surfaces they come in contact with, making them excellent glues. Now that we know how glue works, it'll be easy to understand how tape works, because all tape is an adhesive, which is glue, plus a backing, or a material that the glue is already stuck to. For example, office tape is just a thin layer of plastic, usually polyethylene, with an adhesive spread out on one side. Masking tape is just paper with an adhesive on one side. Duct tape is just scrim, which is kind of like cloth or a woven material with an adhesive on one side and a thin plastic coating on the other. Electrical tape is another type of plastic, vinyl, that's electrically insulating, plus an adhesive on one side. Now all of these tapes mainly differ in what material the backing is, but they can also differ in what material the adhesive is. But just like with the glues we saw previously, they're usually polymers. And here are a couple of examples. A lot of tapes use acrylate as the polymer. And just like with the glues, these molecules have lots of side chains that can attract the surfaces they come in contact with. Now, tapes are a great way to stick things together temporarily, but when you pull them apart, it often leaves a sticky residue. Suction cups are a great way to stick things together without glue. Let's take a look.
Suction cups work because they have this nice concave shape that the plastic, or polymer, remembers, and if it gets distorted, tries to go back to. For example, if I try and push this suction cup against a wall, it flattens. And then when I release it, it tries to go back to its original shape, but it can't. Let's talk about why.
As I mentioned, suction cups work because they're made of a flexible concave material, usually a polymer, that remembers its shape and tries to return to it when it's distorted. Now, when you press a suction cup against a surface, what you're doing is removing the air between the cup and the surface. And when the cup attempts to rebound and regain its shape when you let go, the cup pushes on the surface. That force and the attraction between the cup and surface molecules creates a barrier for airflow. Basically, the air can't flow back under the cup, as long as the surface that you chose isn't too rough or porous. Now, because there's now more air pushing the cup towards the surface than away from it, it sticks. So in essence, suction cups stick to surfaces because the atmosphere is pushing it against the surface. Pretty neat. Do you want to see some other neat examples of just how strong atmospheric pressure can be?
Here's another great example of atmospheric pressure pressing something together. Here, I have a really hot can of water. Right now, the water inside there is boiling, and so pressure, water vapor is building up, and if I plug it, all the hot water molecules that have vaporized are trapped inside the can. Now, hot air molecules take up more space than cold air molecules. So if we cool them down, they'll shrink, take up less space. So the pressure inside the can will be less than the pressure outside the can. And you'll get to see firsthand just how strong atmospheric pressure can be and why suction cups really stick to things.
Go.
Here's another fun example of atmospheric pressure pressing something together. It's too big. Inside this dewar, I have liquid nitrogen, minus 173 degrees. Now, I have a balloon that has air that's room temperature. We saw with our can that when we make air cold, it takes up less space, it exerts less pressure. The normal air outside then exerts more pressure than the air on the inside. What do you think is going to happen? Come take a look. That whole dog fit inside there. I'll zoom back. Do you think we can fit another dog? Let's try. Two dogs in one dewar. Do you think we can go for a third? Whoa! 3 dogs in one dewar. So when I take this out, you'll see just how hard the atmosphere is pressing down on the air inside these balloons. It squished it flat. But now that the air inside the balloon is warming back up, it starts to push out on the atmosphere again. What's it doing?
Reflating it.
It's reinflating.
Awesome.
And the puppy is back. Good as new. Another fun thing to do with liquid nitrogen is see just how cold it is. Instant vaporization. Awesome. And spooky.
Welding is another way we can stick things together without using glue. It's usually how we stick metals together. How it works is that we heat the joint of the two pieces of metal up until they melt and flow together, and then we let them cool. And as they cool, they form bonds. So welding is a very strong way of sticking two metals together. This is how railroad ties are stuck together. They're welded. And there's a really fun reaction called the thermite reaction that they actually use on railroad ties to weld them together. Let's take a look.
This reaction is called thermite. This is actually a way that on the railroad, people would weld railroad ties together, because this reaction makes the iron get so hot it melts and forms together, and then when it cools down, it solidifies into a single piece of iron. So the molecules stick together as we get them so hot and then cool them down. Let's see how we weld things together. We've been talking a lot about how molecules stick together, but sometimes you make a big sticky mess and it just keeps going, and then you need to clean it up. So it's nice to be able to stick things together, but how do we unstick things? Let's talk about that.
We've been talking a lot about how to stick things together, but sometimes you want to unstick things. And how do you do that? I'll mention a couple ways. First, you could simply use a mechanical force to separate things. If you think back to my peanut butter and jelly sandwich, I was able to pull the two pieces of bread apart because I'm stronger than the jelly. But that doesn't always work. So another way to unstick things is to find something that one of them is more attracted to than the current thing it's stuck to. And to be honest, most unsticking methods use a combination of these two methods. For example, your pencil. Inside your pencil is a material called graphite. All graphite is a bunch of carbon atoms arranged in sheets like this. As you scrape your pencil across a page, the graphite sheets stick to the paper. That attraction between the graphite sheets and your paper, along with the mechanical force of you pushing your pencil across the page, is enough to deposit the graphite sheet onto the page. And that's the black line that you see, a bunch of graphite sheets stuck to the paper. If you make a mistake, we all know that you just used the eraser on the end of the pencil to get rid of the graphite. But how does it work? Well, graphite is a nonpolar substance, and so is the rubber. And so those molecules are attracted to each other slightly more than the rubber is attracted to the paper. So as you rub your eraser across the paper, it pulls up the graphite, and to be honest, a little bit of the paper, and makes the graphite stick to the eraser. It's a combination of molecular attraction and mechanical force. But if you rub too hard, you'll tear the paper, so be careful. We're all familiar with rubber pencil erasers. Another eraser that I think is pretty neat, that you might be less familiar with, is melamine foam, otherwise known as magic eraser. It does some pretty neat things. Let's take a look.
Now, I know none of you would ever write on the wall with crayon, because I'm sure your mothers have told you not to, and it's a bad idea. But maybe you have a younger brother or sister who doesn't know better yet. Uh-oh, it looks like someone here has written on my wall in red crayon. What do I do? Well, we learned earlier that crayon is a nonpolar material, so if I try to use water to get it off, not much happens because the crayon doesn't stick to water. I need something else. Luckily, people have discovered something called melamine foam. You might know it by the term magic eraser. It is basically like fine-grained sandpaper, and I can use mechanical force to loosen the particles of crayon on the wall. Now, melamine foam is also extremely porous, and so if I wet the foam first, the loose particles of crayon that I've just dislodged from the paint are suspended in the water, and then the water gets sucked up into the foam and away from the wall. Good as new. All right, we just talked about a magic eraser for your wall. Now, let's talk about a magic eraser for your body. You ever make a mess and just get a little messy? Hold it straight out. You just get a little messy. Sometimes we make a mess, don't we? And then we try to wash it off. Then we try something clever to try and wash it off, and oops, we just make it worse. Oh my goodness. Well, let me show you the magic eraser for your skin, at least with this chemical. Vitamin C, good on the inside and on the outside. All those purple molecules sticking to our vitamin C.
It might be a little. It feels weird.
Aw, clean. Thanks, vitamin C.
Now, let's talk about laundry, because we all spill things on our clothes that we wish we hadn't. How do we get those stains out? Of course, the answer is laundry detergent. But how does it work? Basically, it's soap, and soap molecules usually consist of a nonpolar end and a polar end. The nonpolar end, which is the long chain seen here, is attracted to the dirt or stain molecules in your clothes. The polar end, which is the right side of the molecule here, is attracted to water. So, as you put soap in your clothes, the nonpolar end attaches to the dirt. The polar end is attracted to the water that you rinse through your clothes, and it leaves with the water, pulling the dirt with it. Pretty cool. Sometimes, even with laundry detergent, stains can be frustratingly hard to get out, and so you just feel like burning your clothes. Which you can do, because most clothes are made from cotton, which is just cellulose, and which burns. Incompletely, but it burns. Let's take a look.
Sometimes laundry stains are so frustrating that you just want to burn your clothes rather than clean them, which you can do because most clothes are made out of cotton and cotton burns. Incompletely, but it will burn.
Now, instead of sticking something like mustard to our clothes and getting frustrated that we can't get the stain out, we could try sticking something useful or fun to our cotton. For example, we could treat our cotton with boric acid to make it boric cotton. Or we could treat our cotton with nitric acid, which gives a completely different result. Let's take a look.
Now, if you treat the cotton with something beforehand, say soak it in a solution of boric acid and get different molecules to stick to the cotton, something different happens. Is it burning? Come in real close and let's take a look. I'm doing my best to light it, but it's not catching on fire. It's now flame resistant. This is what we do to firemen's clothes. We treat it with boric acid. It becomes boric cotton, and it resists flame. Now, we can also treat the cotton with something else, nitric acid. If we do that, it doesn't exactly become flame resistant. If we treat it with nitric acid, we're basically adding the N from TNT. And it burns completely. Let's do that again, just because it's fun. All right, now this is just normal cotton. We just got a few extra molecules to stick to it.
I hope you've enjoyed learning about sticky chemistry as much as I have. The last thing I wanted to share with you were some of the reasons why I stick with chemistry. First, I love pretty colors, and there are so many pretty colors in chemistry. Did you know that each element burns with a different color? Let's take a look.
One of the reasons that I stick with chemistry is because of all the pretty colors. I love colors. And did you know that each element makes its own beautiful color or spectrum of colors? Copper burns a nice, pretty shade of green. Strontium burns a beautiful shade of red. Ever wonder how we get those red fireworks? Most of it's strontium. Lithium also burns red, sometimes purple. Do you notice that the flame is blue? That's because we're burning methane. So the flame by itself is mostly blue because it's methane that we're burning. If you have a gas stove at home, you recognize that color. Gas stoves use methane. Now, have you ever sat around a campfire? What color is a campfire? It's that nice glowing yellow. That's because sodium burns yellow. And sodium is all over the place. our skin, on trees, pretty much everywhere you go. There's sodium in the wood that you burn, and so the fire looks yellow. Let's do something else fun with flames. Do you remember that nice shade of green that we get when we burn copper? Let's see that one more time. Ooh, we got a mixture. Looks like there's strontium and copper and sodium all in a mix. Well, now that we have a nice bonfire going of all of our beautiful elements, let's see what happens when a windstorm comes along. Let's see. Let's see the wind starts turning. Starts blowing a little bit more, whipping around. And all of a sudden we have a flaming tornado. This trick combines two things I love: pretty colors and fire.
Another reason I stick with chemistry is that it illuminates my world. My knowledge of chemistry helps me understand the things that go on around me, and I love that. Speaking of illuminating, let's look at this fun reaction involving the molecule luminol.
Another reason I stick with chemistry is because it illuminates my world. And I can understand things that happen around me. For instance, why this stuff is glowing. I mix these two chemicals and a molecule called luminol lights up. And because of chemistry, I know why. Chemistry illuminates my world. So I stick with it.
And last but not least, I stick with chemistry because I get to blow things up. Let's make one last explosion before we go.
All right, the last reason I stick with chemistry is because I get to blow things up. Thanks so much for celebrating National Chemistry Week with me, and I hope you will stick with chemistry too. Happy Chemistry Week!
If you would like to try some sticky chemistry of your own, here's the recipe I followed to make the slime I showed earlier in the video. And if you just can't get enough chemistry, you should check out the chemistry camps we offer here at BYU in the summers. As soon as it's safe to meet in large groups, of course. Happy National Chemistry Week!